Right. So I wanted to briefly talk about the next homework. I've posted a draft of it, and it'll be now that I changed my mind. The draft describes it as one homework, but in fact, this will be 2 assignments back to back. The general idea here is we're implementing sort of a TCP variant. We're not using TCP. So there's this really handy tool in Linux called TC for traffic control. You can do all sorts of stuff with it for managing queues in your OS for network communication. But one thing that we're going to play with this time is we use this network emulation feature. And it's there just to test programs against kind of network problems, to see, is this robust against these problems, right? Usually, as a developer, you usually have like a nice connection and you know losses, it's fast and so on. And you want this to see, well, is it going to work for someone who's out on a sailboat in the Pacific on a like 500 millisecond link with 10% losses, right? It's hard to test that on your laptop, but here you can set it up pretty easily. So that's what we're going to do. So we set up a variety of different conditions. So here we say, oh, the latency on this link is 100 milliseconds with some variance. So it might go between 90 and 110 milliseconds. We have 10% packet loss rates. 25% of these packets are reordered, like they kind of switch a little bit. I forget the 25 and 50 now, what the 2 are, but anyway. And then the maximum rate on this link is 1 megabit. So you may have a fast link, but in fact the OS will restrict it so that you can send at most one megabit. So if we, and then by the way, when you want to use your machine normally again, you can also remove those conditions. So we're going to use, for testing your solution, we're going to use a whole bunch of different configurations like this. We try something with a really fast connection with lots of losses, a really slow connection with lots of losses, a long latency, short latency, high bandwidth, low bandwidth, right? And your job is to put together a reliable transport protocol using unreliable UDP packets. Right? So there's a very basic expectation here. We have a sort of 2 programs. It will be a template, a very simple, stupid template will be provided that receives packets and puts them out on the standard out. So here we're redirecting it into a file name, and that's usually what you would want to do. Right, so it says, okay, anything that arrives on port this so-and-so, just write it out on standard out with write, not with printf. Right? That's the receiver, and on the sender end, you say, oh, which IP address or host name and which port do we want to connect to and which file do we want to send. Of course, the expectation here is the file arrives on the other end in complete and unmodified as quickly as possible. So the 2 parts of this homework, and it'll be a 2-part homework because it is a relatively large assignment. First one will be to just get it correct. So under many different conditions, make sure you can get the file across. Right? Set up the connection, probably with a 3-way handshake, the way TCP does. Deliver the files over. Wait until you've received the entire file, or until the connection is closed, and then that's about it. And we'll want to manage the round trip time in this homework, so that we don't take forever, right? But other than that, we're not worrying too much about the speed. And then in the second part of the homework, we'll also manage a congestion window, so you can have more than one outstanding packet at a time. In the first one, there's like 1 packet at a time being sent and acknowledged. And in the second one, we'll send many packets, potentially 1,000 packets outstanding, right? Over a long latency, high bandwidth link, you would need to have maybe 1,000 packets outstanding. And then we basically going to measure the throughput to see how much of the ideal throughput are you able to realize with your solution. We could potentially have a little class competition, like try to do something online. Haven't figured out how we can do that in practice, but it'd be nice to have a little website, right, where you submit your binary and an automatic program runs it, and then you get a top list, right? This one got 22 megabits per second, right? So that'd be cool. High scorer, but let's see if we get there. Okay, so in terms of expectations, or you had a question?
Yeah, I was just wondering if reordering would be part of first part or second part. Reordering and losses.
Right, it'll be part of both. It's very easy in the first part. You can't really get reordering in the first part because you only have one outstanding packet, so what's going to happen, right? But you might still have losses for sure. And it gets a little more complicated in the second one when you have multiple outstanding ones. But usually with a cumulative acknowledgement, it'll kind of take care of it.
So we will be doing the packetization of the file.
What's that?
We will divide the file in packets, right?
Yeah, absolutely. Right.
So in 1500 bytes, or is that principle the packet size?
Yeah, it'll have to be a little bit smaller. In order to travel over the internet, the total packet size, not including any link layer headers, can't be any more than 1500 bytes to reliably travel over the internet. So, was there more questions? Yeah, okay. So, there aren't many restrictions on this one, right? Well, other than the normal don't copy paste other people's code, and if you do anyway, put references. But other than that, you're expected to generate these two binaries when you say make these two binaries come out, and we're supposed to be able to run them. And then you can't use any reliable transport or any other kind of communication under the covers other than UDP packets. So say if you were to connect with a TCP socket, of course that'll work, right? But that's not allowed. You also can't do most of the evaluation will be on the single machine, but you can't be reading and writing through files or anything like that, right? It's all the communication, any information that travels between these two machines has to be by just the UDP, not two machines, the two receiver and sender applications has to be by UDP packets. We'll also test this by running it on different machines. It doesn't make a difference in terms of everything except like verifying that there's nothing funny going on. Everything will be the same running on one machine versus two machines, because we're emulating the network using this thing, this traffic control. So we'll have all the difficulties even though we're just on one machine. Okay, right, so if you want, go ahead and write it in Rust. You could even write it in Java if you like. All right. I wouldn't recommend it. It can be harder. You could try Python. Right? As long as Hamed can run it on his machine, maybe you want to verify that he can, that he can do it. Yeah. Other than that, of course we want the source code, and we'll just run it based on, evaluate it based on how it performs. Okay, and then finally, and we'll discuss this a little bit more today, is a bonus version. I would suggest doing this after you've finished the whole outstanding, like the whole second part with a congestion window. This here we're not allowed to make acknowledgements. So we're supposed to reliably send a file to the other side, but there can't be any ACKs. The only packet you can send back is it's done, right? So the receiver says, okay, I got everything, but it can't do anything more. Like after that, it's done. So it's basically, it's not that it's one packet you can transmit, but it's only, you can send the same packet many times if you want, right? But you can't send many different packets from the receiver. There's only one, like stop it, that's it. So how do we do that? And that's the topic of the rest of the class. I think it's a beautiful idea. So this one-way reliable transmission is not necessary if you have a two-way connection with low latency. Then it's much better to do this acknowledge and retransmit. It's usually much simpler and, generally speaking, extremely efficient. You just have a large congestion window and then retransmit whatever didn't make it. It can't get better than that, really. But there's a couple of places where you can't have acknowledgements. The common one that many of you have used, probably not all, is satellite radio, right? So satellite radio, well, I don't know, satellite radio. Yeah, it's not totally reliable, right? It'll sometimes just make weird noises or stop making any sound. If you go in a tunnel, it just stops, right? So it's not quite right what I'm saying. We need forward error correction in satellite radio, but there's no such thing as a reliable file download, right, on the radio. Like, oh, I got the entire file. It's not quite like that. In any case, it's sort of it's a close but not quite accurate approximation. And the other one is if you're transmitting over a very long latency link with losses. And I think one good example would be the various space probes, right? They want to transmit something, and it could actually take like hours before the Earth station can respond saying, oh, you missed one there. So in order to have an efficient transmission there, you would want to sort of anticipate that there will be losses and avoid having those losses rather than having to do a back and forth, because that back and forth can severely restrict the available bandwidth, unless you have an infinite size transmission window, which you don't on these little things that are solar powered. Okay, so those are a couple of applications, but you could imagine you want to download a file over like a firmware upgrade to a car, right? And you want to do it over the FM radio, because there's lots of Earth-based transmitters. It's really long range. It'd be an excellent way to deliver firmware, but unfortunately, you can't get acknowledgements back. Like, there are no transmitters in the car. Transmitter doesn't transmit back to the Sears tower saying, yeah, okay, I got your voice. Right? It's just going in one direction. So how do we manage that? The general idea is to just send more, but let's see what are some options. So reliable one-way communication, also known as forward error correcting codes, FEC codes. Okay, so if this was, let's start simple. We just do redundant transmissions. Easiest possible solution. Send the file over and over again. Right? So, so this is now for the homework setting, right, where there is there's one packet coming back. Even that is a little generous, but without feedback, it'd be hard to know when to stop sending. So you'd either have to guess, sort of have a model for what is the maximum loss rate you could possibly have on this channel, or you would have some sort of feedback. So in this case, we have 1 bit of feedback. Okay, so I send my file, all the packets, back to back. And then, rather than wait for any acknowledgements, I start from the beginning of the file and I send it again and again and again at maximum rate. And at some point, the receiver has gotten all the various packets that it needs for the file, and it sends a bit back saying, we're done, and then I stop. For all of this, because there is no feedback, we don't know anything about congestion control. We can't do congestion control, right? We don't know if we lost a packet, and no one tells us anything about how congested the network is down the road. So we're just going to have to set a rate and stick with it. Okay, so problem with congestion control. So that one we're not going to address, and it's very inefficient. So say in this entire large file, we just lost one packet, right? And now we send the whole file again, and probably it's fine. Like, what are the chances? If there's 1,000 packets in this file, it's a 1.5 MB file, so it'll be 1,000 packets. Pretty slim chance that the same packet will be dropped again. So now the receiver gets 2 copies of everything except the 1 or 2 packets that kind of got lost in either copy. But let's see. Copying the entire file, right? So to make this a little bit more concrete, why don't we break it down into, there's 3 packets. It's a smaller file. There's just the 3 packets for now. And we want to transmit it, so let's see. So we could transmit ABC. Let's go like this. So it looks like ABC, ABC. But maybe on the receiver side, we receive like A, C, A, B, right? So we lost, out of each transmission, we lost 1 packet, 33% packet loss, right? Out of each transmission here, we lost 1. Packet loss doesn't really work this way. It's not like it's completely uniform. Usually it'll be bursty. You're losing a packet because the queue is full, or because there's a pigeon in front of the antenna, or something like that. So it'll be bursty to some extent. There's ways to address that, but for now, let's just imagine it's uniform random losses. Okay, so now, how do we decode this? Actually need a sequence number as well, right? So each packet would need to have a number in it saying what's its name, all right? But we anyway have sequence numbers in reliable transmission protocols, so that's fine. So now we have 1 of each, and we got 1 extra. That's okay. So now we had to transmit 6 to get 3 across. That wasn't so good. So an alternative is called using parity. Parity packet. So this is a simple one. Let's start with a simple one, and then a more advanced one is called a low density parity check, so LDPC code. But the basic thing we could do is, if we know that we have 30% packet loss, we don't necessarily know what the packet loss is going to be, but let's say, in this case, we have a known error rate. So then we should have this code needs to have a rate of 1 extra packet per 3 packets. For a good code, we'd be able to then get our original message. If we receive any 3 out of 4 packets, we'd be able to get the original message. So we send A, B, and C, of course, because that's easy. And then we need to send 1 more packet, such that if we lose one of one of these three, we can decode what that packet was. And the solution is to send A, XOR B, XOR C. So that's one packet, right? So you just take all of the bits of the packet, just XOR the whole thing bit by bit. We assume here that all the packets are the same length, but you could really pad it with zeros at the end if you wanted. So if it's set up this way, right? Say we receive A and C, and then this thing. Now how do we get B?
Do A XOR B XOR C, and then XOR A and C with that big one.
Exactly. So we had, that was one packet. So the beauty of XOR, you take anything, XOR A, right? It either flips the bit twice, or it doesn't flip the bit at all, right? That's what XOR does. If it's a 1, it flips it. If it's a 0, it doesn't do anything to it. So flipping a bit twice returns it to what it used to be, so you can always just XOR again to make A disappear. So A XOR A makes the A part go away. And then C XOR C makes the C part go away. And there's B. So this is sort of the standard approach for parity. You may have seen it in, if you were doing, give me a moment, maybe in 362, if you took that, maybe you're doing some serial communication. I don't know. The parity bit there works the same way, except it's all the bits in one byte. So you got 8 bits, and then you XOR all of them together, and you get the last one as a parity bit. That doesn't tell you which bit was wrong, though. It just says, like, the parity bit checks whether everything is okay. In this case, the packet comes with an identifier, so we know that, oh, I don't have B. And that's how we know that we can XOR with A and C to figure out which one, what was the value of B. Yeah?
So when you figure out that you're missing B, are you hoping that the sender is also going to tell you where B goes in the packet?
Oh, no. So, okay, so I'm using A, B, C here, but it's really like offset 0, offset 1500, offset 3000, right? So we know where it goes. We know, yeah. It's just a little easier to write it like this. Okay, is that clear? Yeah.
Could you put the way you XOR to get B again?
Okay, actually, maybe we should let's see, use the programmer's calculator. Let's try this. So let's say we have A equals 5. These are very short packets now, right? But it's exactly the same. Okay, so if you want a packet that is more than 1 byte, you just tack more of them along and treat them byte by byte. There's nothing special there. We could even do it bit by bit, but kind of isn't that fun with the programmer's calculator, at least. So actually, why don't we do a bit by bit first? Okay, so A is 0, B is 1, C is 0, and then it comes with it an identifier saying, like, which bit is this? Right? Otherwise, we can't do it. We need to know which one we lost. And then the A XOR B XOR C, what is that? Anyone? 1, please. We have 1, 1. Zeros don't change anything. All right. So that's a 1. Okay, so now we know that we lost B. This is really key. Otherwise, we can't do anything. So now we take our value A XOR B XOR C. Well, so that's the 1. And we XOR that with the 2 that we have to remove those. So we XOR it with 0 and XOR it with 0 from that one. And that's 1. So now we know that B was a 1. Right. And this works for any combination of values. In fact, yeah, I take this back with the programmer's calculator. It'll just be more confusing. there's no interaction between the bit at offset 1 and the bit at offset 0 when you XOR bitwise. So we can just deal with this as pretend that it's only 1 bit, but it works just as well with any length packet. Okay, so this is called an erasure code. Right? It doesn't fix if B got corrupted, so that B changed from a 0 to a 1. That doesn't work. So the solution that we rely on, there's 2 different ways you can do it. You can use an error correcting code. Those are more complicated and usually not worth it for long packets. So what you do instead is you put together a check to see whether the packet arrived correct, like it contains what it used to contain, and then an erasure code for in case the packet didn't arrive at all. And then if the packet arrived broken, well, then you throw it away and pretend like it didn't arrive. So an error correcting code, error detection. I'm not going to do error correcting codes here, but error detection you can do with CRC32 is a very common one. Or you can do like that checksum in TCP, right? Add up all the bytes in the whole packet and just put the sum at the end, modulo 256. So now you get the packet, then the packet arrives, you add up all the bytes to see if the sum is the same as the sum that arrived with the packet, then you're good. Checksum, as in TCP, is a really stupid way to do it. It's really not efficient. Or like accurate. No, it's accurate, but it'll lose many, it'll not detect many errors. Whereas CRC32 is also fast and much more efficient at detecting errors. In any case, once we've detected an error, we throw away the packet and we treat it as a complete loss. Okay, so this is excellent. Parity packets like this is excellent if you have a 33% packet loss rate, right? In fact, we can do a little bit better, right? For any, if we know what the loss rate is, we just use more of them, right? You take ABCD, now you can handle 25% loss rate. ABCDE, you can do 20%, right? So pretty much any loss rate, as long as it's pretty uniform, we can do okay. If you lose 2 packets though, like if you lose A and B out of here, this doesn't help you at all. Now there's nothing we can do. So you probably need to code a little bit harder, right? That, maybe you expect to lose 1 packet every 10 packets, but we do a code like this so that we can handle one loss every 3 packets, and then we're able to recover from even more than 1 packet out of 10 occasionally. But it's not completely robust. We can do much better with a little bit of clever math. So the sort of typical one that they use for spacecraft and stuff is called a Reed-Solomon code. And there the general principle is we're based it on math rather than just XORs. We base it on a little bit more complicated math. In this case, it's a polynomial. So we're saying, let's do this again, our ABC, right? But we want to be able to pick more values. Like we want to be able to have any arbitrary redundancy So we want to be able to send lots of different packets, all unique packets, but they all describe the same data, this 0, 1, 0. So what can we do? We can form this function of x for x is a value between 0 and something. We say x minus a. Oh, this doesn't work very nicely for binary values, really. Right. So this polynomial is 0 for x's that are the solutions to the polynomial, right? So for any x where the value equals one of those packets that we wanted to transmit, it'll be 0. But what's really nice about this is you can send out f, and yeah, it's problematic that we only have 0 and 1 here. So now we have to pretend that these are byte values instead, or this wouldn't work. So for x in 0 to 255, let's say. So now we can send f of 0, f of 45, and f of 67, and these three uniquely identify this polynomial as just out of math. So if we have any three, no matter for which x, as long as they're unique ones, we can figure out which polynomial was it, and then we have the solutions to the polynomial that is sort of what the polynomial is. And so now we know what all the values were. So if you want like 100-fold redundancy for this thing, you just send 100 packets with 100 different x's. Just send out what the value was of this function, and on the other end, whatever the trick is to decode it, I forget. Just figure out what was the polynomial that corresponds to it. We'd have to know the degree, of course. Right? We know that it's of this form, and we have to know what the degree is. But after that, we can compute it. So now you get really arbitrary redundancy if you know the rate of the rate of losses. Then you can just kind of adjust it and say, oh, we lose 5 out of 14. Well, let me send 19 packets and then move on. Okay, this is still for known loss rates. If we don't know the loss, then it gets a lot more interesting, and this is called a Luby transform for unknown loss rate, or it's called a rateless code. Unfortunately, we're out of time. I think I'll spend a little bit of time on this next time, but the general principle for the Luby transform is just like this simple one. Reed-Solomon code is cool, but it takes forever to decode, a little problematic. This one is really fast and nice. But what we do is, instead of saying, okay, every 3 packets, I put one that's XOR of all 3, you say, okay, let me pick a number. This time, every 5 packets, let's XOR those together. This time, 18 packets, right? And the next time, I take a few of the packets from the beginning of the file, a packet in the middle, a few here, so you just pick random packets out of the file, 7 of those, and then I pick just 1 packet, send that one, and so you pick like a random collection of packets and XOR them together, and at some point you have enough. So if you pick a clever distribution where you have some where you send an XOR of everything, oh, this is a good example. Say we lose every other packet, and then sometimes we lose one more packet. What we really should do is send an XOR every other, and then an XOR of everything. Right? Then we can get our original data back. So in a Luby transform, that's the general idea. Some very broad XORs, some kind of small XORs together. And at some point, the receiver has everything they need to compute every packet, the contents of every packet, and then we're done. So that's what I was hoping you would do for the bonus solution. It's not actually that complicated. It's complicated to get it optimal, not that complicated to get it to work. Okay, so I mentioned on Piazza that office hours are truncated today. We'll start at 4:30. If there's a lot of people, we can extend it a little bit past 5. All right, see you Wednesday.